51, I should be able to give you the masses, the angle, and you can figure out which way it's going to go. Requires trig beyond the scope of this course, even though a large number of you have had some trig at least. I would need to give you more information for you to know the answer which way friction is going to act. There's not enough information here. And the main reason I do that is occasionally on a test I do bad proofreading and you end up with a situation like that where it could go either way. Well, we passed the first ideal. The second ideal is someone's going to ask before anyone hands it in, and then I can put a correction on the board. If no one asks, then I'm left with the, well, it could go either way, so I have to count. So for this, let's assume that it's going to move this way. Why? Just because I said so. Definitely, I could set up a situation where it's going the other way. So if it's moving that way, the way I've indicated right there, which way will the friction act on mass 1? I assume you mean down the ramp.
Yes.
And so there's one acting up. And another hint, when you're dealing with friction, friction requires normal force. We will get to that in chapter 4. But I have normal force in only 2 places. So friction could only possibly exist in 2 places. It exists here. It's not going to exist here because we're dealing with ideal and they're frictionless. Manal, is that a question?
Would the friction be on the pulley and the rope? On the circle thing?
The circle thing? I made them ideal.
Oh, right, okay. Right.
If the pulley, because in the way this situation is set up, the circle thing is just going to sit there and the rope's going to slide over it. If I did add a friction there so that the pulley turned, then yes, there would be a friction, and the rope is going this way, so the friction acting on the pulley would be, let's see, friction's going this way, so on the rope it would be acting that way, and on the pulley it'd be going this way. But we're not worried about that right now, unless you want to. Okay. Any questions at the moment? Because we're ready for a test level problem. True story.
Wait, so there's no second friction here? On the second block?
It's not touching anything other than the rope,
okay.
and that we're calling tension.
Okay, right. We know we have 2 touching surfaces.
If I had made this side of the ramp, steeper so that mass 2 is sitting on top of it, then yes, there would be another friction. Fair.
So for tension, I'm kind of confused about where you place the arrows. If they're acting towards each other, why wouldn't you put the upward arrow on the rope and the downward arrow on the box?
All right.
Like you do.
So if I have something hanging from a string, now some people can imagine this and some people aren't. Are you okay with just imagining? All right, so you agree that there's weight pulling down on this. If I cut the string, what's the mass going to do?
It's gonna drop.
Right. So there must have been, while it was attached to the string, there must have been something holding it up. That's what's holding it up.
Okay.
Is that sufficient for now?
Yeah.
Okay. You can look at it this way, is that, remember you put the force on the receiver of the force, not on the source. So the rope is pulling up on the box. It's holding it up. Other questions at the moment? All right. Time for a test level problem. Do this every time. All right. Like this. Dad pulling boy on sled. If you don't like the inherent sexism of dad and boy, feel free to make it mom and daughter, or if you wish to mix it up. I guess we can make it sinister. Kidnapper pulling. I have drawn this better before. This is horrible. Tyrannosaurus Rex arms. All right, hopefully your own drawings will be much more true life. All right, so on a test-like problem, I'll give you the situation. We will have them accelerating this way. Acceleration is to the right. And I will give you the diagram of it broken up. So we have the sled. We have boy, ground, rope, dad, so 5 objects. And I will recommend we do friction last. Friction is the trickiest one here. This is disturbing me. I'm not changing the problem, I'm just changing my drawing. Slightly less disturbing, but not by much. It's like a balloon attached to it. Questions on what the problem is? All right, with what do we start?
Weight.
All right, which way is weight acting on what?
The weight of the boy is acting down on the sled.
You said down on the boy?
Down on the sled.
Weight of the boy will not be acting on the sled at all.
Down on the ground.
The weight of the boy down on the ground? So draw my arrow like that.
Up on the ground, sorry.
All right, so this is weight of boy. Where's the other? Down on the boy, all right. Weight of boy. All right, one down. Weight of dad. Weight of dad. Yep. Weight of sled. Weight of sled. And anything else with weight? Assume ideal rope. Weight's done. Oh, can we get rid of anything? Most of the times on the complex force diagram problem that you'll have on the test, I think there's been one exception. Usually there's others eliminated. All right, so weight's done. What now? Okay, acting which way on what?
Down on the sled.
And what's causing that down on the sled? Okay, so down on the sled. Which way is it acting on the boy then? Yep, someone's got to be holding them up. Let's see if this will work. There we go. Try to do some sort of color scheme here. And is that it?
Down on the ground and up on the sled.
Okay. Now, in terms of drawing this, I have it just basically clipping the very end of this. If you drew this arrow out here, I would assume you meant it's part of the sled. So just, if you drew it in the middle here, I have no idea what you mean, as talked about last time. And if you drew it, you know, the pair of arrows like that, not actually touching the object, I wouldn't assume that, you know, it's separated enough, assume that's on the sled and that's on the ground. But there is some gray area where I do have to make that judgment call, and it's just nicer if I don't have to guess. All right, anything else? Any other normal forces?
Normal force between dead and the ground.
Anything else?
There is friction between the slide and the
Any other
ground.
normal forces? Any other normal forces?
No.
All right, Nadine says no. Let's do friction last. So what's the other force we need to deal with before friction?
Tension.
All right, which way is tension acting on what? Okay, I would hope so. Which way is it acting on this end of the rope?
Yeah.
So pushing up on this end?
Yeah.
Or,
Would be down.
So the
Yeah.
sled.
they're pointing like that, so it is, tension's a pulling force, so it's gonna be pulling on the ends. And so we have this tension here. Where's the other part of that pair? I think somebody just said it. It's like, all right, that was close to unison, that was nice. And it's attached to the front of the sled, okay? And I've already drawn the arrow here. There's some tension here. Again, it's an ideal rope, so these don't need a subscript. Where's the other part of this pair right here?
That's on the dad's on.
Okay, which way is it acting on dad? Give people a chance to write this down, then I'll talk about the most common mistake I see here. This is just a drawing of the separate pieces. I tried to draw it in the right orientation, but it's not perfect. Some students will recognize there is a force between the end of the rope and Dad's hands, and they will mistakenly draw it like that. The force is not acting in that direction. It is, yes, acting between the hands, but remember the hands aren't really this far down below the rope. So the tension is acting up at that angle and down at that angle. All right, so we have only one rope. We got tensions at both ends. We are done. If you want subscripts, then we got this would have this, on the left would have the same subscript, and on the right would have the same subscript. But the subscripts are optional. And now, friction. Let's do the easy one. Remember, friction requires a normal force, so we have normal force between Dad and ground, boy and sled, sled and ground. So those are the only places that friction could possibly exist. So let's start out with sled and ground. Which way is friction acting on the sled?
To the left.
That-
That way.
Up and down.
Sled.
We got three different answers.
No.
Sled is moving that way.
Yes, sled is moving that way.
Yeah.
So friction is acting this way. Opposite, yeah.
There's friction acting on the sled that way,
And the right.
opposing that relative motion, because relative to the ground, the sled's moving to the right, and so therefore there's also a friction acting this way. All right, that's the easy one. Let's do boy and sled. Next.
He's not moving on this, like, he's just sitting on the sled.
It's not a question of whether he's moving or not, it's a question of which way would he move. If this were frictionless, which way would the boy move relative to the sled?
To the left.
If- So therefore, which way is friction acting on the boy? There has to be a net force in the direction of acceleration. We'll talk about that in chapter 4 in far more detail. But there's indeed friction acting to the right on the boy, and therefore acting left on the sled. That's wrong subscript there, that should be a D. So we'll do our sled and boy. Boy's sitting on the sled. If it were frictionless, this thing would be slipped out from underneath him, like the tablecloth trick. So if the sled's, because the sled's getting pulled out from underneath him, relative to the sled, the boy is moving backwards. So if he starts here, relative to the sled, the boy wants to go backwards, and therefore friction is preventing that. Or there has to be some force accelerating him to the right. Friction is it. And so now, the questions on that before we talk about Dad. All right, which way is friction acting on the Dad? Okay, to the left, so, got another vote for left?
Left.
We have 3 votes for left. I think that's 4. Let's see physics by democracy. See how well that works. All right, so friction on Dad. So this is the force that we're drawing on Dad, not on the ground, but on Dad. So we've got left, right, or there is no friction acting on the Dad. Okay, so have an opinion, even if it's completely unfounded and you're going with your gut. Don't base it on what other people said, base it on your own gut. Who says friction on Dad's to the left? 1. All right, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 saying to the left. Who says to the right? Who says there is no friction on the deck? I think, Naveen, you're the only one who didn't vote.
There is no friction between the dead and the slide and the roof.
So there's no friction between dad and the
No
rope?
friction, yeah.
Well, there's tension here. I'm talking about between dad and ground. Because dad's touching the ground.
Mm.
What's your gut tell you?
Yeah. Okay, there is a friction and left and right. The dead from the dead go left, from the ground go right.
So on the dad left?
Yeah.
Okay. So you're unanimous. If the friction is acting that way, which I think was it what everyone said. What force, because the net force has to be in the direction of acceleration. As mentioned earlier today, and explored later, what force is going to the right? There has to be some force to the right if he's accelerating to the right. All right. The silence is either one of two things. One, you didn't understand the question, or two, you have no idea what the answer is. Both? All right. There has to be, the total force has to be in the direction of acceleration. That's just one of those physics things. Newton's second law, more specifically. I said in the beginning of the problem that acceleration is to the right. Therefore, there has to be, the total force acting on any object has to be to the right. So therefore, what force is acting on the right, to the right on the dad? I will just go ahead and assume that the silence means you don't know what the answer is. All right? It actually is friction. He goes to the right because of friction. But doesn't that contradict what I said earlier about friction opposing relative motion? The dad's moving to the right, so how can friction be in the same direction? Here's how.
I've got a question.
Yes,
Is there no friction from the buoy to the sled?
there is.
Not
That's,
the buoy, but like from the dad to the sled?
no.
Okay.
In order for there to be friction, there has to be contact. We are assuming no Jedi powers here. All right, so this will be, how stable is this table? Ooh, that's actually probably one of the better ones. To date, there's been only one table that's ever collapsed in here. Fortunately, no one was on it at the time. While I still can. If you ever work for DuPont, do not do this. I was working with DuPont, and the surface I had for a desk was in parts twice as wide as this. It was sort of triangular shaped. And I was kneeling on it, perfectly safe, kneeling on it, peering over the partition to be part of a conversation. They stopped the conversation and said, "You need to get down." I said, "I'm perfectly safe." They said, "No, you need to get down now." DuPont does not mess around with that. I know there are other companies, but DuPont was the one I'm more familiar with. I saw the injury statistics for 1 year. This is for a full year worldwide. 12 injuries among DuPont employees, 12 injuries among consultants or visitors. The most serious injury was somebody stepped off of a sidewalk wrong and twisted an ankle. I worked with US Steel for 9 months. 1 death, 1 broken arm in that 9 months. And that is that's actually just at 1 plant. So anyway, don't do this if you work for DuPont. You will be written up. Most people who worked with DuPont have that story the first time they were called down for about holding the hand railing while going down the steps. I was not reported, I was just told. You gotta have your hand on the handrail. All right, so as I'm risking my life to do this for you. Think about when I walk. I have my foot touching the piece of paper here. As I step forward, which way does the paper go? Yes. The friction on the paper was backwards, but the friction on my foot was forwards. The relative motion here is not the dad, but the foot. The foot is pushing backwards. And so in a reaction to it, the friction acts forwards. Similar thing with tires. If you think about in terms of tires, if you've ever been stuck in mud and you gun the engine, the tire spins, mud is flung backwards, which means the friction on the mud on the ground is backwards, so the friction on the car is forwards. That's why the car goes forwards when you're on pavement or something like that. Unless you have a Ford, then it's a 50-50 toss whether it's actually going to move at all. You know, I shouldn't judge all of Ford by that one piece of crap that I had. Or should I? Anyone else have a Ford? Okay. Maybe there's a reason that no one else in here has a Ford. So it's the foot. And this is one of the reasons why I had the front foot in the air. That's not an amputee there, that the foot is just down. Because actually it floats back and forth. As I walk, I have friction pushing forward on my back foot. As soon as my front foot touches, imagine that you're doing this on ice. My front foot would actually slide out forwards. So there's friction acting back on my front foot. I stand up to this point, there's no friction acting on my front foot once my center of mass is right over it. And now friction's acting forward on my left foot here. And friction actually will flip back and forth between the 2 feet.
It's like during races when the runner has to put his foot on that little thing to push himself.
Oh, on the starting block?
Yeah, is that?
That's a normal force there, because the starting blocks, I think they're usually something like that. So there's going to be some friction. If he's pushing that way on the block, then there's a normal force which would be perpendicular to that, and then there's a friction which is going to make up the other piece of it. I don't think they're perfectly vertical. Anybody here run track?
They're at an angle.
They're at an angle? Okay. Do they teach you to push forward or push sort of up?
I actually never used them. I just saw other people use them.
Okay.
And I think you more press with the front of your foot against more towards the bottom of the angle.
Okay. I haven't used them in decades. More specifically, since the mid-70s. Right. Anyway, we are done. This is a test level problem. On a test level problem, I think the fewest number of forces is somewhere around 20, and the most I've ever had was around 40. So just give you some idea. Questions? All right. Again, there will be a complex force diagram problem, not that one, on the test. Probably the second to last problem on the test, more specifically. All right, so we did earlier about sort of summing up forces here. So let's say I have a force pushing to the right on a box, and just sort of get into the habit, let's make it a 5 kilogram box. And to give you some idea what 5 kilograms is, you have a, there we go. That's a 5 kilogram mass. And let's say that it's to the right of 4 newtons. So just given this, now I haven't given any context here. In a problem like this, we are not assuming that there's a planet, unless I said it's on the ground or something like that. Do not assume that there's a planet anywhere. So our force diagram is basically that. That's our force diagram. This is an example of other. I haven't told you what causes this force. I just said that the force exists. If I wanted to write the total force, now if I'm writing total force, I can write net force, or I can write total force, or I can write a little, that's a capital sigma with a force. This is a capital sigma. And it means sum. In other words, you add them all up. Again, math people and physicists, mathematicians and physicists want to write as little as possible, so they come up with these symbols. Now, most textbooks will not put any of that stuff down. All they're going to do is just write force. And you're supposed to know that this means total. So how would you express the total force acting on this 5 kilogram mass? All right. 4 what?
4 newtons to the right.
Okay. So 4 newtons to the right. You want me to write out to the right?
Or I hat, if we're assuming that means to the right.
All right, so you want to make I hat that way? Okay. So we need to actually say I hat's to the right. Okay, there we go. Then I hat. Now, I have my 5 kilogram mass here, and I have 4 newtons acting to the right, and I have 4 newtons acting to the left. You can keep the same convention if you want. What is the total force now?
0.
Give me the whole thing.